So this is the lecture when things start to get a little bit weird and take what you might think is a bit of an unexpected turn. So try and stay with me while I go through this. So let's talk about just a simple flat plate under a tensile load. Here we go. There we go. Flat plate there, and tensile load applied. And now, let's say that I asked you to tell me what the stress was here at location A. Well, that's pretty easy to do for you now. You take a section cut through the object like this, draw the free body diagram. Here we go, and you've got a force here. You know that you have an internal normal force that equals F there. Point A is right here, and you can see that we've got only a normal stress at point A. So if I was to draw the little element of material that was existing at point A, right, you'd have that little element of material down there where the side of the element that's in the section plane is that side there, and we have a normal stress sigma like that. Okay, no big deal. But here's the interesting thing. I'm trying to blow a piece of hair off my iPad screen there. Here's the interesting thing. Nobody said you had to take a section cut like that. You chose to take a section cut like that because it facilitated calculating what the stress was at that point. But you didn't need to take that section cut. You could have taken a section cut that was oriented something like that. So what would that have given you if you looked at it? Okay, well, okay, we've got a free body diagram that looks something like this, where we've got a force F, and we know that we have to have a force that is equal to F in the opposite direction, but you always want to put your internal forces on parallel and perpendicular to a section cut so they can be properly defined as normal and shear forces. So the vector sum has to add up to this, so we'd have a normal force component and a shear component. So here's N, here's V, and here's point A there. So now we've got an internal normal force and an internal shear force. So if we look at the small element of material that's located at point A, there it is again. This side is in the section plane. What are we going to have there? We're going to have a tensile normal stress sigma acting on that side. And then we're also going to have a shear stress tau acting downward on that face that's in the section plane that's resulting from that internal shear force. And then, of course, we'd have a couple of more shear stresses on the other sides to balance those out. So remember, these two pictures that I've drawn here, these both represent what the stresses are at point A. I'm just going to move this down a bit and label it to hammer that point home, right? So this is point A here, and this is also point A here, okay? And you know, well, what if you took a section cut like that there? Well, now you've got a free body diagram if you were to draw it. Right, there's your section cut. You've got force here, force there. Right, point A is located right there. Oh, there you go. Your free body diagram is in static equilibrium now, so there's no internal forces. So this drawing says that there's no stress at point A at all. So that's odd. So the key here, you can see that the stresses that exist at point A are changing based on the orientation of analysis, right? The orientation that we take our section cut at partly defines what the stresses that we report existing at A are. And this is the idea of stress transformation, the idea that the stresses that exist at a point are dependent upon the orientation of your analysis. And to really fully define the stresses that exist at a point, we need a way of being able to represent all these various combinations of stress that can exist at a point based on your orientation of analysis. And that's where this tool, this graphical tool called Mohr's circle, comes in. So let me show you how Mohr's circle, just again conceptually, is related to what we've just looked at here. So if we were to sort of sketch that situation again here, just quickly do that. So we've got, and this doesn't hurt to just see this, not that it was anything visually remarkable, but just to let the sort of concept sink in here. If here was our object and here was our point of interest, okay, so that's point A there. And what we want to do now is we want to create, for all the different section cuts that we could possibly do, we want to create a graph that maps out the different combinations of shear stress and normal stress that we get for every section cut. So let's create this graph sort of, let's not do it in red, let's do it in black. Let's create that graph over here. And we'll just put normal stress on the horizontal axis and shear stress on the vertical axis, right? So if we take our first section cut, so that's just our normal orientation section cut, and I'll just draw what the free body diagram again looks like down here. Okay, so for a section cut like this, we've only got an internal normal force N, right? So at point A, what do we have in terms of stress? Well, we just have a normal stress and we have no shear stress. So we've got a point on our graph here, somewhere there, and we've only got normal stress, no shear stress. Now, because this was a section cut that was in the sort of the normal horizontal orientation, let's label that as the 0 degree section cut. So this is 0 degree section cut. Okay. So now if we take another section cut, right, like one that's, fairly horizontal, but not quite, then what we're going to get for our free body diagram is something like this, where we have our force here, and we know that when we split the vector up into its perpendicular component and its parallel component relative to the section plane, we've got a normal force and a shear force here. And if that angle of our section cut, right here, this angle is theta, and if that angle's small, then the normal force is going to be quite small in comparison to the shear force. Okay. So the normal stress is going to be quite a lot larger than the shear stress, but the normal stress won't be as big as the normal stress for our 0 degree section cut. So we're going to have a slightly smaller normal stress, and we're going to have some shear stress now. Not a large amount, but some. So we've got a new point right here. Right now, as we increase the angle theta of our section cut, what's going to happen? Well, that normal stress vector is going to get smaller. The normal force vector, is going to get smaller, and the shear force vector is going to get bigger again as we increase theta. So what's going to happen? Our normal stress is going to keep shrinking, and our shear stress is going to keep increasing. Okay, so we're going to get another point in here that looks something, like this, where we get an increase in those stresses. And then now let's take it to the extreme and say, okay, well, what happens when that angle is 90 degrees now? So that's point A there. So now we're taking, we've taken cuts here that have become, a little bit steeper, more inclined, and now we're going all the way to that vertically oriented section cut here, where we've got our point A here, and our force is F, and there's no internal forces present now because our object's in static equilibrium. So this is our 90-degree cut here. Right, section cut 90 degrees relative to our original 0-degree cut. And now we've got 0 shear stress, 0 normal stress. So now we're back at the origin, right? And if you actually map this out and continue to actually calculate what the value of sigma and what the value of tau is, in this case, tau is not associated with an internal moment. So you calculate the shear stress tau is simply V over A. And if you do calculate those for multiple different angles of section cuts, what you get is a curve that looks like this, that follows a circle. Okay, and this should be passing through all those points, but you get a semicircle. And then if you continue and turn your section cuts the other way, and go past 90 degrees, start going back down to 0 degrees the other way, well, what happens is your normal force doesn't change. You still have a tensile normal stress, but your shear stress changes directions because your section cuts are oriented in the opposite direction. So you get the other half of this graph, and you end up with a perfect circle. And now this is really bothering me here because the side isn't actually circular. Okay, so that's better. So there we go. So this should be our dot there that we drew the second time. There we go. So you get actually a circular graph from that. And that graph is called Mohr's circle. So over here, this was our 90-degree section cut. Right, so this circular plot is called Mohr's circle. And what that plot does is the points on the circumference of that circle give you all the possible combinations of normal and shear stress that exist at point A for all different orientations of analysis that you can choose. Okay? So we've gone from a situation now of having, one definitive answer for, what is the stress at point A, to a situation now where there are an infinite number of possibilities of what is the stress at point A. And all of those possibilities are captured by Mohr's circle. And all of the combinations of shear and normal stress that can exist at point A are only fully represented by this circular plot, or this plot that gives a circular shape to it. So what I want to take you through is just, again, a teaching by example sort of type problem where I take you through the steps of how to plot Mohr's circle, and then we talk about what that means. But first, we need to set up some rules for what's going to be a positive normal stress and what's going to be a negative normal stress and what's going to be a positive shear stress and what's going to be a negative shear stress, because we're plotting shear and normal stresses now on an XY graph that has both positive and negative sides of the axis. Okay, so sign convention for Mohr's circle. Okay, so the first odd thing to know with Mohr's circle is just how the axes are set up, and this is always done this way just by convention. So the axes for Mohr's circle are set up like this, where you've got an x and a y axis, and the horizontal axis is normal stress, so plot normal stress along the horizontal axis with positive normal stress acting over to the right, and we'll talk about what positive normal stress is in a moment. But normal for that. For shear stress is plotted on the vertical axis, and by convention, positive shear stress is always oriented downward. Okay, so that's something to keep in mind here when you're doing Mohr's circle, is that positive shear stress is oriented downward. So now, what is positive and negative in terms of normal stress and shear stress? Okay, so a positive normal stress is a tensile normal stress. So if we have a stress like that, this is a positive value of normal stress. Okay, so tension is positive sigma. And then, of course, if we had a compressive stress, right, that's a negative value of stress. Okay, so we've got compression is a negative value of normal stress. Okay, for shear, what we have to do is, for shear stress, you look at the element's right-hand side, and if the shear stress is acting upwards on the right-hand side, then that is a positive shear stress. So if the shear stress is acting upwards on the right-hand side, it has to be downwards on the left-hand side, and then to the right on the top and to the left on the bottom for those complementary pair of shear stresses, and that's a state of positive shear stress. So positive tau is upward on the right-hand side of the element. And then, of course, now that you know that, you know what a negative state of shear stress looks like. Again, you always look at the right-hand side, and if the shear stress is downwards on the right-hand side, then that's a negative shear stress. So there we go. So now you know how tensile and compressive normal stresses in different orientations or different directions of shear stress are plotted on the axes of Mohr's circle as positive and negative values. So with that set up, now let's look at a simple example where I'll show you how to plot Mohr's circle. So it's really easy to plot, actually. Okay, let's get rid of that. So example. All right, we're just going to have like pretty much the exact same scenario that we were just looking at. Okay. And we'll make it a three-dimensional problem like this. So this is a flat bar, and let's give it some dimensions here. Let's say that this width is 100 millimeters, and the thickness here is 4 millimeters. And we don't need to worry about its length, but we'll have it under a load of 5 kilonewtons. 5 kilonewtons. There we go. And what we want is to plot Mohr's circle for point A right there. Now it doesn't really matter where point A is, since this is an object that's just under a tensile load, so all points in the object experience the same state of stress. But you're always drawing Mohr's circle to represent the state of stress at a particular point. So we'll label this as point A, the one that we're particularly looking at. So to draw Mohr's circle, so steps for drawing Mohr's circle. Okay, so the first step here is to define the stress state of the element that's located at your point of interest. So that's what we worked on in the last lecture, defining the stress state of the element that's located at your point of interest. So define stress state of element at point of interest. Great. So this can be, like a fairly lengthy process, this first step, or in simple cases, it can be, an easy process. So for us here, what we're going to do is we're going to take a section cut through the object at our point of interest here. So what have we got there? We've got something that ends up looking like this. Okay, where we've got our 5 kilonewtons and our 5 kilonewtons there, and we've got our point A right there, and then we'll draw the volumetric element that's located at point A. So again, this is the small volume of material that is located at point A. Here we go, put on the hidden lines. Now, the face of this element that's in the section plane that I've cut, so the section plane is where I've actually cut through the object, that plane there. The face of the element that's in the section plane is the bottom face here, and the rest of the element goes up into the remainder of the free body diagram. So the stresses that I place are on that section plane. Now, we've only got an internal normal force here. That's 5 kilonewtons. So we're going to just have a tensile normal stress resulting from that tensile normal force. So that tensile normal stress gets placed right here. And this is sigma due to our normal force N. And there's its equal and opposite pair. Okay, now the value of sigma subscript n, very easy to calculate. Sigma subscript n is n divided by A, which is 5,000, multiplied by what? 0.1 for the width and 0.004 for the thickness will give us 12.5 megapascals. Okay, so that's step one. Now, what we should do now is we should really, and we should have done this to start with, but we should really define a coordinate system for our problem here. I shouldn't say we need to define a coordinate system for our problem. So let's make the vertical axis our y-axis, the horizontal axis here our x-axis, and then coming out this way we'll have our z-axis. And then we'll put those over here too. So we've got our y, our x, and our z. Okay. Now our normal force, sigma subscript n here, this is our only force, so there's no stresses to combine. So what this really would be more appropriately labeled as the stress in the y direction, sigma subscript y. Now, we're going to have stresses with y as a subscript now, since we're dealing with multiple directions, and we need to start getting careful about labeling the orientations of our stresses. So you're going to have to pay attention about not confusing these sigma subscript y's with the yield strength or the yield stress of the material that we're dealing with. This subscript, sigma subscript y, is the normal stress in the y direction. Okay, so what we're going to do now, so that's step 1. Now, Mohr's circle, you draw Mohr's circle based on a 2-dimensional in-plane element, not a 3-dimensional volumetric element. So a 2-dimensional in-plane element is just the 2-dimensional view of a 3-dimensional piece of material. And you want to take the 2-dimensional view that captures all of the stresses that you've drawn on the element. That's a good way to explain it for this point in the course, or just, I should say, for this course. So let's go to the next page and write that down as the next step. So to draw in plane version of our volumetric element. Okay, so let's go back and we'll grab our volumetric element here. Copy and paste. Okay, there we go. And let's just get rid of that. We know that's going to be more appropriately labeled sigma y, and that's megapascals down. Okay, so let me just grab this and create a label so it's better for you in terms of taking notes. So this is our volumetric element, and this is at point A. Okay, so this is the volumetric element at point A. And then what we're going to do is we're going to represent this as a 2D in-plane element at point A. So in-plane element at A looks like this. So we want to draw a 2-dimensional view of this 3-dimensional cube of material that captures all of the stresses that exist on it. So we could either choose to draw this element looking down the z-axis, and we'd still see that normal stress sigma subscript y, or we could choose to look down the x-axis, and we'd still see that normal stress sigma subscript y. What we couldn't do is draw this element from the viewpoint of looking down the y-axis, because then we wouldn't see that stress. For a 2D in-plane element, the stresses have to act on the edges of the element for them to be seen. So let's draw it looking down the z-axis. So if we look at it down the z-axis, then we have, for our axes that we've set up, we have x and y like this, and our stress just appears like this, where we have sigma y equals 12.5 megapascals. Right, so there's our in-plane element. It's called an in-plane element because that element is that's the view in the XY plane. Okay, so we've done that. So I'm going to, again, just copy our in-plane element, and maybe I'll even take the name with me. There we go. And we'll come over here. Now we're looking at step 3. Okay, so step 3 is to calculate what the average normal stress is that exists on the in-plane element. Okay, so Mohr's circle is always plotted based on a picture of an in-plane element. So this is the picture here that we're going to be plotting Mohr's circle based on. But the first step in really plotting the circle is calculate our average normal stress sigma average. So what our average normal stress is just like it sounds. It's the average of the normal stresses that are acting on our element. So it's 1/2 of whatever the normal stress is in the horizontal direction plus whatever the stress is in the vertical direction. And I'm avoiding here putting subscripts x and y, so you don't always think it's the x-axis and the y-axis that you're averaging. It's just whatever the two directions are that you've got in your in-plane drawing here. So for this example, right, or for the current example, what we've got is sigma average is 1/2 sigma x plus sigma y is 1/2. Now the stress in the x direction is 0, and then the stress in the y direction is 12.5, and it's a tensile stress, so it's positive, right? If that was a compressive stress, it would need to go in that equation as a negative. Okay, so now we've got what, 6.25 megapascals for our average normal stress. Okay, now what the fourth step is now we have to set up the axes of Mohr's circle and plot the average stress, and the average stress is the center point of the circle. So step 4, set up axes for Mohr's circle, plot sigma average, which is circle's center, and I like to label that C. Okay, so let's do that. So we have got, now maybe I'm going to use straight lines here so that this looks nice. Okay, there we go. So we've got positive normal stress that way and positive shear stress downwards, right? Don't forget that weird sign convention for setting up your axes for Mohr's circle. Okay, so what do we have from the last page, right? I'm going to grab, this is probably still on the clipboard actually. Let's see. Paste, there we go. So there's our in-plane element, and we've already said that the average normal stress for this is 6.25 MPa, right? And that goes to be labeled point C, the center of our circle. So let's plot that. That's a positive 6.25. So that's maybe somewhere on our axis right here, 6.25. So we're doing this in megapascals on both axes. Okay, so we put a dot right there, and that's the center of our Mohr's circle. Now, the center of your circle is always going to lie on the horizontal axis. So the center point is defined by coordinates of sigma average, comma 0, if you're thinking about the coordinates in terms of normal stress, shear stress. The center point of the circle is always sigma average, comma 0. All right, in order to plot a circle, the other thing that you need is you need a point on the circumference of that circle. And if you've got the center point and a point on the circumference, then you've got your circle constructed. So I'm going to take everything here, and we're going to do the next step. Okay, copy all of that. Okay, paste. Okay, and we'll just erase all of this up here. And this isn't step 4 anymore, this is step 5. Okay, so what we're going to do now is plot what's called our reference point on our reference point, and this is labeled point A, on the circle's circumference. Okay, point A. Let's get rid of a couple of things down here, and we'll get rid of that now. I've reiterated that this is an in-plane element, enough to kill that. Okay, so point A. Point A, our reference point on the circle's circumference, always has, well, every point on the graph has some coordinate, sigma, comma, tau, but the coordinates of point A are given by the stresses on the element's right-hand side, okay? So what we do is we take our in-plane element, we identify the right-hand side there, and we write in this notation what the stresses are. So there's no normal stress, okay, and there's no shear stress on that right-hand side. So that gives the coordinates of our reference location, point A. So here is point A. They're right at the origin, 0, 0. And maybe actually I'll do that point in red just to emphasize that that's our reference location, point A. Okay, so now we extend the radius of the circle from C to A and label that R. That's the radius of our Mohr's circle. And then we can get our compass out and we can draw that circle. So let me see if I can draw a decent circle here. Okay, not too bad. That should not be poking through on that side of the axis at all. Let's see if I can get it a little bit better. There we go. Perfect. So there's our Mohr's circle. Okay. So let's talk about, so this 0, 0, this is just specific for our example. So for our example, right, A equals 0, 0. So again, you're plotting what the stresses are on the element's right-hand side. Okay, so let's talk about what Mohr's circle gives us now, and let's do that by just taking the circle that we've created here and copying it to a new page and looking at it in relation to our original object. Okay, so our original object, right, looked like this. Okay, there we go. And point A was right here, point A. And we had drawn the in-plane representation of point A like this, where we just said we had sigma subscript y because this was our y, x, y, z directions. Okay, and this is the element's right-hand side. All right. What Mohr's circle does is give you all the possible combinations of shear and normal stress that exist at point A in this object. Okay, that's under this 5 kilonewton tensile load. So the way that it's used is like this. So you take point A here, and you can imagine moving point A around the circumference of this circle to wherever you want to go. And as you move point A, what you are doing is you are taking this element here inside at location A inside that object, and you are rotating that in the same direction as you move around the circle, but by half the angle. So, for example, let's just take the easy example here. If we take point A and we rotate it all the way around to the other side of the circle right here to location A prime, okay? That's 180 degrees in the counterclockwise direction. So what that's equivalent to is looking at what happens when you take this element that we've got right here and we rotate that by half of that angle, but in the same direction. So we rotated that now by 90 degrees so that what was our right-hand side here, our right-hand side, I don't want a thick line, our right-hand side is now at the top. Now you'll see that point A, right over here at the origin, gave us what the stress was on this right-hand side of the element, right? At the origin is 0, 0, 0 shear stress, 0 normal stress, and those were the stresses on this right-hand side. If we rotate 180 degrees around the circle, which is equivalent to rotating our element by 90 degrees, the coordinates of point A prime now give us what the stresses are on that side of the element when it's in that orientation. And we can read those right off of the graph here. If the center of our circle is 6.25, our reference point A, is located at the origin, then this point over here must be double, so it's 12.5 megapascals. So we know that the stress here is 12.5 megapascals. Okay? And of course, that's giving us the value of what sigma y was, 12.5 megapascals, right? So no surprise there, but what it tells you is that the stresses that are on the two different sides of the element, the normal stresses that are on the two different sides of the element, are given by points on the circle that are separated by 180 degrees. Now, if we instead move point A to, let's say, a point that is located right here at the bottom of the circle, so let's call this A double prime. So we go from point A to that point on the circle. That's a rotation of 90 degrees around our circle. In reality, what that is a rotation of our element by 45 degrees in the same counterclockwise direction. So that's equivalent to what we'd have if we had analyzed the stresses at point A with a section cut oriented 45 degrees. So going from our original element here that we drew Mohr's circle on, if we take that element and we tip it up by 45 degrees, 45 degrees. And this was the right-hand side previously, so now that's the right-hand side there. The coordinates that are at A double prime give us the stresses that are on that right-hand side of the element when it's tipped 45 degrees. Again, this is, let's say theta equals 45 degrees, and this is 2 theta is 90 degrees. Now, the reason that a 90-degree rotation on the circle corresponds to a 45-degree rotation when you're actually thinking about the orientation of the element, and that's the case. Any rotation on the circle is always twice the value of what the rotation of the actual element is, or the orientational rotation that you're looking in reality. And the reason that is because if we go back to the very start of this lecture, you'll remember that when we changed our section cut from 0 degrees to 90 degrees, we went from one side of the circle all the way to the other side of the circle. So changing our section cut angle by 90 degrees caused a 180-degree rotation around the circle. So all the rotations around the circle are always double what the actual changes in orientation in reality. So let's go back here. So again, the stresses that are on this right-hand side that we've drawn are given by the coordinates of A double prime. And we know what the coordinates of that point are. We've got an x-coordinate of 6.25, and that's a positive value, so that gives us the normal stress that's acting on this side. So this is sigma equals 6.25. In terms of naming here for stresses, if we had an x-axis and a y-axis, and then we tilted them, this is now the y prime axis, and now this is the x prime axis. So this is sigma x prime is 6.25. And then the shear stress on that side is given by the y coordinate of that point right here. And that y coordinate is going to be equal in magnitude to the value of the radius, which is 6.25. So this is going to be 6.25 down there. So now remember that that is a positive shear stress, so that means it acts upward on the right-hand side. And right-hand side, you're talking about what the original right-hand side was. So this red shaded side, you can imagine that side of that element always stays shaded red as you're rotating that element around. So this here is tau x prime y prime, and that is equal to 6.25 megapascals as well. And then we know we have to have another normal stress there and another shear stress there, and matching shear stresses like that. Now what I've just drawn there isn't a complete description of what the stress state on that element is, because we're missing the normal stress on these other two sides. And you get the normal stress on those other two sides by imagining that you're going to rotate this element a further 90 degrees, so that red side moves up to there, and that from where we currently are on Mohr's circle is equivalent to taking our point from A double prime and moving it 180 degrees around the circle to the top here. And if we read off what the x-coordinate is there, it's also 6.25. So that means that the top of this element has to also have a tensile stress. That sigma y prime is 6.25 megapascals of tensile stress. Okay? So that's the sort of way Mohr's circle works. You can take point A, and starting from your reference point, your reference location, you can move it to any point on the circumference you want, and whichever point you land on, the XY coordinates of that point give you the stresses on the right-hand side of the element as it's rotated in the same direction you're rotating on the circle by, but by half the magnitude of that rotation, by half the value of that rotation. Okay, so let me redraw Mohr's circle, and we'll talk about what a couple of different points are called here. So again, try and draw straight lines here. Okay, and then our circle went through the origin and around like that. That's not great. We can do better. Let's try one more time. Here we go. You know what's the easier way to go? Let's draw our circle first, and then let's draw our axes. There we go. Okay, so we had the center point of our circle, which was point C here, the reference point, which was point A, the radius of the circle stretched from C to A. Now, and our axes are labeled positive normal stress and positive shear stress pointing downwards. There we go. Okay, different points on the circle. Okay. The top and bottom of the circle, so this point up there and that point down there, those represent, as you imagine moving point A around the circumference of the circle, when you get to either of those points, those define what the maximum shear stress that exists at a location is, right? So this is the maximum shear stress, tau max. Okay, so you can't get a larger shear stress at a location than this. So for our situation where we had something just under a tensile load here, and we were looking at a particular point, and we said that the in-plane element looked like this, where we've got normal tensile stress. This means at that location, if we wanted to know what the maximum shear stress was, that maximum shear stress could be achieved by rotating down or up by 90 degrees, counterclockwise or clockwise by 90 degrees to either one of those points of tau max. And that's a rotation of 90 degrees, which means that's a rotation of 45 degrees in reality, and that's equivalent to taking a section cut through at 45 degrees. So the plane here of maximum shear stress at that particular point, point A, we wanted to draw the element that experiences maximum shear stress, it would be oriented at 45 degrees relative to the horizontal, right? And that's exactly what we've just drawn here. So this was the element that experienced maximum shear stress because we drew it at point A double prime. Okay, the points that are on the x-axis, so where the circle crosses the x-axis or the normal stress axis, those points, when you're at those, you have normal stress but no shear stress. So these are what are called the principal stresses, and they're always labeled sigma 1 and sigma 2. Sigma 1 is the one with the larger absolute value, and sigma 2 is the one with the smaller absolute value. So sigma 1 and sigma 2 are called principal stresses. So an element that is experiencing principal stresses experiences zero shear stress. So element that experiences principal stresses has no shear stress acting upon it. Okay, so that gives you the basic idea of Mohr's circle. So that's probably a little confusing to follow. It'll become clear as we do some examples and you see it put into practice. So let's do an example. So this is going to be kind of similar to the example that we did when we were looking last lecture at defining the stress state in an object. So what we're going to have is, but just a little bit different. That's supposed to be a circle there. Okay, that's almost better, but not quite. Okay, there we go. Okay, so here we've got a rod that's fixed, and let's give it some dimensions. So this is going to be our 100 millimeter rod again, and let's say that it's got a length of 4 meters, and let's put some loads on it. So we've got an axial load this time. F is 50 kilonewtons, and then we'll put that torque that we had on it, T 3 kilonewton meters, and the point of interest for us this time is going to be right here, point A. Actually, because we're going to have an A on Mohr's circle too, let's label this as point B so we don't get confused about which variable is which here. Okay, so the question here is the following. We want to define the element at point B that experiences maximum shear stress. So define element at B that experiences. Let's do principal stresses as well. Good practice. Experiences A, maximum shear stress, tau max, and B, principal stresses. And those are given by sigma 1 and sigma 2. Principal stresses sigma 1 and sigma 2. And their maximum shear stress, tau max. Okay. So in order to define the element that experiences those stresses, maximum shear stress of the principal stresses, what we need to do is we need to draw, we need to plot Mohr's circle for point B in this object. And to plot Mohr's circle, we first need an in-plane element that's a representation of the stresses that occur at B, and to get the in-plane element, we need the volumetric element that defines the stress state at B. So let's work on getting that volumetric element that defines the stress state at point B first. So let's change this into a free body diagram first of all, just by erasing that support there, and then I'm going to put my axes on here like this, and now I'm going to label them. So I'll label them X, Y, and Z there. And now we want to do our equations of statics to get our internal forces. So sum of the forces in the x is already 0, sum of the forces in the y is already 0, sum of the forces in the z, okay, we need a internal force like that, that's 50 kilonewtons as well for those to balance. That's perpendicular to the section plane that we've taken. So this is an internal normal force there. And now we can think about our moments. So moment about the x-axis, there's nothing that creates a moment about the x-axis now, so we're okay there. Moments about the y-axis, no forces creating a moment about the y-axis. Torques about the z-axis. Yes, we need a torque about the z-axis in this direction. T subscript z is 3 kilonewton meters. So now we want to sketch our element of material that's located at point B. Here we go. And identify the face of that element that's in our section plane. So our section plane, right, is the back face there. And that is the back face of that volumetric element that's in the section plane, and the rest of that element is projecting into the body of the rod down the z-axis. Worth redrawing our coordinate system, just so we don't make a mistake here. Okay, so looking at our internal forces, we've got a compressive normal force, so that's going to apply compressive normal stress here. So this is sigma subscript n. And then we've got what? The shear stress resulting from a torque. So if we look at the two-dimensional view of that cross-section, like this, where our y-axis is pointing upwards like this, and our x-axis is pointing over, that internal torque is around in that direction. So point B here is going to be sheared tangent to the circumference and in the direction of the torque. So that's a shear stress that is pointed in the negative x direction. So we just go to our cut face, or our face of the element that's in the section plane, and add a shear stress in the negative x direction. So like that there. So this here is tau subscript z, or tau subscript tz, sorry. Tz. There we go. Okay, so we've only got one normal stress and one shear stress acting on that volumetric element. So we can calculate what those values are and redraw it with the stresses properly labeled. So let's do that quickly. So we've got sigma subscript n is equal to n divided by a is what, 50 times 10 to the 3 divided by pi over 4d squared, 0.1 squared. And that is giving a value of 6.4 megapascals. Then we've got tau from Tz, T rho over J. And what do we have there? We've got 3,000. Our value of rho, how far we are from the axis of rotation, that's the radius, so 50 millimeters. And J pi over 2 radius to the 4th power, like that. And that's going to give us 15.3 megapascals. Okay. So now we can redraw our element with those stresses appropriately labeled here. So there we go. Perfect. So what did we have? We had one normal stress that was compressive. Okay, now let's take our coordinate system with us. We've got x, y, and we've got z. So the stress that I'm drawing is a stress along the z direction, so it should be labeled sigma subscript z, and that's equal in magnitude to 6.4 megapascal. 6.4, that better 6 to read, 6.4 MPa. Okay, and then our shear stress was pointing over this way, which means that we have one on the front face like that, and one on that face, and one on that face, and its value, or its label, is tau. It's the face that it's on is perpendicular to z, and the shear stress is parallel to x, so it's tau zx, and its value is 15.3 MPa. Okay, so now we've got to take this volumetric element and represent it as an in-plane element in order to draw Mohr's circle. And in order to see all of the stresses that are acting here, what you could do is you could either view it from the top looking down or from the bottom looking up, and you'd see both those normal and those shear stresses acting around the edges of your 2D in-plane element. So let's view the element from the top looking down. So in that orientation, my axes are like this. So I've got Z and X relative to my original, and my 2D in-plane representation of that 3D volumetric element is like this, where sigma z is here, sigma z is 6.4 MPa, and tau zx is like that, and then we've got another one, another one, another one. So tau zx is 15.3 MPa. Okay. So now we're in a position where we can draw Mohr's circles. So let's set up our axes first. So okay, there we go. And we've got positive normal stress, positive shear stress downwards. These are both going to be in megapascals, since that's what our unit of stress is that we're dealing with. Now let's take this and just shift it a little bit like that. Okay, so when we're plotting Mohr's circle, the first thing that we want to plot is the center of the circle, which is given by the center point is given by whatever our average normal stress is, comma 0. So the center of the circle always lies on the horizontal axis. So let's calculate what our average stress, average normal stress is here. So it's 1/2 in this case, sigma x plus sigma z. Remember, 1/2 of your horizontal and your vertical normal stresses. 1/2 sigma x. Sigma x is 0. Sigma z is 6.4, but it's compressive, so it's negative. Okay, so here we've got 3 minus 3.2 megapascals for our average normal stress, which means that C is located at minus 3.2, 0. So let's go ahead and plot that. So we'll put minus 3.2 on right about here, 3.2, okay, and that's our point C. All right, now the other thing that you need to plot the circle is point A, and point A, remember, is given by the stresses on the element's right-hand side. So you just highlight the right-hand side like that, and then say that point A is sigma comma tau for the element's right-hand side. And for us, that is, there's no normal stress on that side, so it's 0, comma. Now, the stress has a magnitude of 15.3. In terms of our convention for positive and negative shear stress, positive shear stress acts upwards on the right-hand side, that acts downwards, so this is minus 15.3 there. So we are going to, for point A, 0 on the x-axis, and then we're going up to minus 15.3. Remember, upwards is negative. So that's our reference location, point A, which describes the stresses on the right-hand side of our element. Now, our radius of our circle connects C to A. So there's radius R for the circle, and of course you can calculate what radius R actually is very easily. Okay, let's see. So now we can draw the circle, right? So let's see. Yeah, that doesn't look too bad. So there's our circle. In terms of what we want from it, let's take it to a new page now that we've got it sorted out here. Okay, copy that, move it to a new page. So, and then let's just go back and look at what we actually wanted from the problem. So the first thing we wanted was what our maximum shear stress was. Okay, so let's go back to our circle. So our maximum shear stresses always occur at the top and the bottom of our circle. So there's the two locations where tau max occurs. Now, in order to go from point A, where we currently are, this is right on the circumference of the circle there, to our maximum shear stress, the easiest thing to do is just rotate over this way to get to that tau max, right? So we're going to rotate by an angle of, let's just say, theta there to get to tau max. So our element, remember, we had an element that was originally looking like this. That was the right-hand side. Now, in order to go from A to our new point over here, A prime at tau max, we are rotating counterclockwise by theta. So it means we have to take this element and rotate it in the same direction, right? So you imagine that it's pinned at this end here and has been rotated up. And if that angle that I drew on here was theta, then this angle here has to be 1/2 of that, because the rotations in reality are half of what they are on the circle always. Okay, so now we need to put our stresses on this element here and figure out what the values are. So the first thing to do is figure out what the value of the radius of the circle is. And I'm just going to move this up a bit here. Right. Okay, so the radius, that's trivial to figure out. So we've got the square root of 3.2 squared plus 15.3 squared power of 1/2 gives us the radius, which is 15.6 megapascals. So tau max, the value of the maximum shear stress, is equal to the radius of the circle, which is equal to 15.6 megapascals. So let's plot that on our circle. So the maximum shear stress is negative, so that means it's downwards on this side. So there we go. And like that there. And let's move the angle label here so we don't get screwed up by that. Okay. So this is tau max equals 15.6 MPa. So now this is becoming the element that experiences maximum shear stress, but we haven't fully defined it because we haven't shown all of the stresses that occur. So the normal stress that exists on this right-hand side is given by the x-coordinate that exists at point A prime. So that's minus 3.2. So we know that minus 3.2 is a compressive stress. So we know here that we've got a stress that is 3.2 megapascals, and it's a compressive stress. Now, we don't indicate the negative 3.2 because, remember, indicating a negative value for a stress indicates that your vector that's representing that stress is in the wrong direction or should be reversed. So this here, the fact that we have a minus 3.2 on Mohr's circle is consistent with having a stress shown as a compressive stress on our actual element. Now, in terms of labels, what was our axis set up like? So we had x to the right and z downwards. So here we've got x and z. So this should be labeled when we rotate this, right? We're rotating like that, and this becomes axis x prime, and this becomes axis z prime. So this is sigma x prime equals minus 3.2. And now remember, for the normal stress on this other side here, which you don't get through point A, what you need to do is imagine yourself taking the element that we have and rotating it around by another 90 degrees, which corresponds to a rotation by 180 degrees on our circle down to a double prime here. And the x-coordinate of that gives you the normal stress on the other side of the element, which is also 3.2. And that's a compressive stress. So we've got, this is sigma z prime is also 3.2 megapascals. And of course, it always happens that the stress is on those two sides the same, because when you've got the, well, it always happens that the stresses on those two sides are the same when you're in an orientation that experiences maximum shear stress, because they pass right through the center of the circle, going from one to the other. Okay, let's see. So the only other thing that we need to fully define the stress state of this element that experiences maximum shear stress is the angle of inclination, right? And we said that that was 1/2 of the value of theta. So that's easy to get. We can get what theta is. That's just the inverse tangent of what opposite, which is 3.2 over adjacent, which is 15.3, and that gives us 11.8 degrees. So 1/2 theta is 5.9 degrees. Okay, so that picture that we've just drawn there, that is our answer for part A. This is the element that experiences the maximum shear stress, right? That's the stress state of the element that experiences the maximum shear stress fully defined. Okay, so let's draw the element that experiences principal stresses now. So that's the second part that we were asked. So let's just flip to a new page here, and we'll just paste back on our Mohr's circle that's not too marked up here. And principal stresses, again, are the stresses that exist when shear stress is 0. So we've got one of our principal stresses here and the other one over here where the axis, where the circle intersects the normal stress axis. The larger of the two absolute values is the first principal stress, sigma 1. Let's get rid of the constraining me to shapes. And the smaller is sigma 2. And again, very easy to get those values. You just take the center point and subtract or add the radius. So our value of sigma 1 here is the value of our center, subtract our radius in this case. So what do we have? Minus 3.2 subtract our radius, which had a value of 15.6. 15.6. And that gives us 18.8 minus 18.8 megapascals. And then sigma 2 here is just our center point plus the radius, minus 3.2 plus 15.6 gives us 12.4 megapascals. So I've got those. Now we just need to think about which way we need to rotate to get to our principal stresses. I always like to rotate by the smaller angle, so we could take point A, which exists here, and rotate it down to sigma 2 and put it right there for point A double prime. So that would be a rotation that is clockwise by, let's say, angle phi. So thinking about our element, what we want to do is take it from that original orientation that it was like that with our right-hand side like this, and we're taking that and we're rotating it by angle phi clockwise. So our rotated element looks like this here, where that right-hand side is there, and then our angle phi is like this, except that that's 1/2 the angle phi. So if our right-hand side here went from being this side to being this side, then the coordinates of A double prime give us the stresses that are existing on that right-hand side, which we know the stress existing on that side is only sigma 2, which is a tensile stress of magnitude 12.4 megapascals. So we've got that here. So this is 12.4 MPa, and this is sigma 2, our second principal stress. So then we've got that there, equal and opposite. And then in order to get the stress, again, that is acting on the other side of the element, what you need to do is imagine taking this and rotating it 90 degrees, which corresponds to going from A double prime all the way around the circle to sigma 1 here. So sigma 1 is the stress on the other side, and that's a compressive stress with a value of sigma 2 equals 18.8 megapascals. And remember, when you have an element that's in a state of principal stresses, shear stress is 0, because both of these points, sigma 1 and sigma 2, have shear stress coordinates of 0. So now all we need to do is figure out the value of phi. So what phi is the inverse tangent of 15.3 over the distance we are away from the center. So we've got over 3.2. And that is equal to, let's just see here, 78.2 degrees. Okay, so we've got 1/2 phi is 39.1 degrees. Perfect. So again, this picture here is the fully defined stress state of the element that experiences principal stress. Okay. All right, there we go. So that picture, those stresses, that angle, that's the answer for part 2. Okay, so I hope that gives you at least an introductory level, a decent level of introductory understanding to Mohr's circle, and then we'll develop that more through some tutorial problems and some more examples. Okay, I will see you again for lecture 15 when we start talking about failure theory.